All right, let's get right into it. We're tackling one of the biggest, most mind-bending mysteries in all of cosmology. The question is simple: what is holding our universe together?
So here's the core of the problem. When astronomers look out at distant galaxies, they see something that just shouldn't be happening. The stars, way out on the edges, they're whipping around so fast that the gravity from everything we can see, all the stars, the gas, the dust, it's not even close to being strong enough to hold on to them. They should, by all rights, just fly off into the void. But they don't. They just keep on spinning.
And this is where it gets really, really interesting. Because solving this puzzle, well, it's not just some academic footnote. The answer, whatever it ends up being, could force us to completely rewrite our most fundamental ideas about either matter or gravity itself. The stakes couldn't be higher.
So how do scientists even begin to explain this galactic-sized mystery? Well, for the last few decades, one explanation has really dominated the field.
It's a pretty elegant idea, actually. The universe isn't just what we see. It's filled with a mysterious, invisible substance called dark matter. It doesn't give off light, it doesn't reflect light, we can't see it at all. But it has mass, and that means it has gravity. In this picture, galaxies are like glowing islands sitting inside these huge, invisible halos of dark matter. And it's all that extra gravity from the halo that's holding everything together. This idea is the bedrock of what we call the standard model of cosmology.
But here's the thing. The dark matter story, as neat as it sounds, isn't perfect. When you really zoom in and look at the details, a pretty big crack starts to appear, and it's right at the heart of the galaxies themselves.
This crack has a name, the cusp core problem. Now, it sounds a little technical, but the idea is actually super simple. Computer simulations that model how dark matter should behave make a very, very specific prediction about what the center of a galaxy should look like. And, well, that prediction doesn't match what we actually see out there in the cosmos.
In this slide, this really shows you the conflict in stark relief. On the left, that's the prediction from dark matter simulations. See how it shoots up into a sharp peak? That's the cusp. It predicts that dark matter should be incredibly dense right at the galactic center. But now look at the right. That's what we actually observe in a lot of real galaxies. It's not a peak at all. It's more like a flat plateau, a core. And this isn't some small nitpicky difference. It's a fundamental mismatch between the theory and the real world.
So this problem, along with a few others, has led some physicists to ask a much more radical question. What if we've been on the wrong track this whole time? What if there is no dark matter? What if our understanding of gravity is wrong?
And this is that alternative idea. It's called modified Newtonian dynamics, or MOND for short. It was proposed way back in 1983, and its core idea is, well, it's revolutionary. It says that Newton's and Einstein's laws of gravity are great, but they're incomplete. In places where gravity gets incredibly weak, like the far-flung edges of a galaxy, the rules of gravity actually change. It's not about adding more matter, it's about getting more gravity.
Now, I know what you're thinking. That sounds a little out there, right? Changing the laws of gravity? But here's the thing, and it's a huge thing. MOND has had one absolutely stunning success, something that the standard dark matter model really struggles to explain.
It all comes down to something called the radial acceleration relation. Basically, what astronomers found is this incredibly tight, direct link between the gravity you'd expect from all the visible stuff in a galaxy and the total gravity that you actually measure. The really crucial part is this. MOND doesn't just explain this relationship after the fact, it predicts it right out of the box.
And wow, just look at this plot. This is where MOND really shines. Every one of those blue dots is a real measurement from one of 147 different galaxies. And that red line? That's not a line of best fit. That is the exact prediction made by MOND. The data just falls right onto the line. It's breathtaking. For dark matter to do this, you need all kinds of complex, chaotic simulations to just happen to spit out this incredibly simple, tight relationship. MOND just gives it to you.
And the precision here is just nuts. This quote from the research paper, that term intrinsic scatter, that's just a physicist's way of asking how much do the data points wobble around the prediction? And the answer is they barely wobble at all. That number is tiny. It means the real-world data hugs the MOND prediction almost perfectly, and that is very, very hard to explain if dark matter is the answer.
Okay, so MOND looks amazing, right? Case closed? Well, not so fast. Because as good as it looks on the scale of a single galaxy, MOND has its own set of really serious problems when you start to push it.
Remember how perfectly MOND worked for individual galaxies?
Well, when you zoom out and look at these giant clusters of galaxies, hundreds or thousands of them all bound together, the picture falls apart. You can see it right here. Those black dots are the measurements from galaxy clusters, and they are way off the line. MOND helps. It reduces the problem, but it doesn't solve it. Even in MOND, you still seem to need some kind of extra unseen matter to hold these clusters together.
But you know what? That's not even MOND's biggest problem. The most devastating blow might come from right here in our own cosmic neighborhood, from our own solar system. Because it seems MOND is being asked to do two completely contradictory things at once.
And this is the standoff. To explain that beautiful, tight relationship we saw in galaxies, MOND needs the change from its modified gravity back to normal gravity to be really smooth and gradual. But when we look at the incredibly precise orbit of Saturn, thanks to the Cassini spacecraft, we find that gravity in our solar system is perfectly Newtonian. And for that to be true, the MOND transition has to be incredibly sharp and sudden. So, which is it? It can't be both. This isn't a small discrepancy. The data from galaxies and the data from Saturn are in what's called a 9 sigma conflict. In physics, that's basically a deal breaker.
So you have two competing theories, and both have these huge successes and these glaring failures. You'd think there would be some kind of tiebreaker experiment to settle the debate, right? Well, scientists thought so too, but what they got was just more confusion.
The big idea was called the wide binary test. It's simple, really. Find pairs of stars that are orbiting each other, but are really, really far apart, right here in our own galaxy. They're far enough apart that the gravitational pull between them is super weak enough that they should start to feel that MOND effect. It should have been a clean, decisive test. Do their orbits follow Newton, or do they follow MOND?
And here's the messy, beautiful reality of how science actually works. Different teams of scientists, often using the very same data, came to completely opposite conclusions. Some studies, like the one you see on the left, found absolutely nothing unusual. The stars were behaving exactly as Newton would predict. But other studies, like the one on the right, found a clear 5 sigma signal that looks a whole lot like MOND. It's a total head-scratcher.
So, how on earth does that happen? Well, it turns out this is just an incredibly difficult measurement to make. There are so many things that can trip you up. Maybe there's a third, tiny, unseen star in the system messing up the math. Or maybe it's not a real binary at all, just two random stars that happen to line up from our point of view. Or maybe, and this is a big one, different teams are just cleaning and analyzing the data in different ways. The really tricky part is that almost anything that contaminates your data tends to mimic the exact signal you're looking for.
Which leaves us right here, in a scientific stalemate. You have dark matter, which works beautifully on the grandest cosmic scales but gets messy inside individual galaxies. And then you have MOND, which perfectly predicts the behavior of those individual galaxies, but seems to fail in clusters and in our own solar system. Right now, neither theory can claim victory.
So we're left with this profound question, one of the biggest in all of science. Is the key to unlocking the cosmos some new invisible type of matter that makes up most of the universe? Or is the answer a radical new understanding of gravity itself, the very force that anchors us to the Earth? It's an incredible mystery. And for now, the universe is keeping its secrets.